Okay, regression. Let's choose this PDF file. When I use PowerPoint, these two lines somehow it just go outside the boundary. Okay, linear regression. First step, we will talk about analytical solution. Okay, quickly, linear regression is when you have many points and you want to find a line that pass through every point or as close as possible. Least means square error. Same thing that you did in Excel. You did, everyone know Excel, right? You just have several points in Excel. You do the graph, curve fitting, and you add trend line. You know it, right? Yeah, you should be able to do it. Okay, then we talk about regularization. L1, L2, and the combination between L1 and L2, which is elastic net. Data preparation, scaling, the scaling matter. Okay, coding the model, making the pipeline, making user-defined estimator, model performance, train test, validation, learning curve. This kind of thing is like using Python library. Use the right Python library. It's too boring to just tell you the curve fitting. So we have multiple x, right? You don't have just one x. You have linear regression, but it's multiple variable. We have linear regression, but you may fit step by step. So let's say, okay, let me show you. At the very end, we do something like this. Continuous updating. So I have data. This the whole data look like this. This is the whole data. It have noise. Okay, this is the whole data. I split it into several parts. Okay, I make my model see this part first. That's the part 1. Do linear regression, and then make it see part 2, part 3, part 4, part 5. See one part at a time, and then do linear regression and see if it can come up with a solution. It can. It's not that perfect, but it has through every line. Why do we need to do something like this? What if you want to do continuous history matching? So once you do history matching, you get the data, you get a prediction. From the prediction, maybe 10 days later, you get more data. You want to use your new data to tune your model, right? And when you have your new data, you tune model, have new data, continuously tune your model so that you have perfect prediction. If your model needs the whole data, 100 lines at a time, you cannot tune your model. But if your model can accept 20 lines at a time, okay, day 1, I have 20 lines, I give that prediction. Next day, I add another 20 lines, and I have a better prediction. Next line, I add another 20 lines, I have another prediction. So this will be more fun, right? It's really regression, but it's better, I think. It's more fun that way. Okay. Let's start with the closed form, the analytical solution. With the regression, we try to model the data with the linear combination of your function. So, regression model F is the linear combination between constant multiplied by phi x, which is a function value. If your phi x, phi 0 is 1, and phi 1 is x, and you have m equal to 2, j from 1 to 2. So your model is a linear combination of beta 050, beta 151, like this. You end up with this. That is line. Right? Linear model, linear equation, just one line. Mx equal to y equal to mx plus b. That's just one line. Okay? So this means beta 1 is slope, beta 0 is intercept. So boring. Okay. What about we have data x1, x2 until xn and have y value. So this is just one data point. So this case, I try to show you what is this x1, x2, x3. So if we have several x, what do we do? So let's take a look at this. And later on, we have a table. Okay. So this case where we have multiple variables. So we don't have just 1 and 2. We may have beta 353, beta 54, beta 555, and so on. For one data point, you need to know x1 value, x2 value, until xn value, and you need to know y value. That's one data point, right? Just one data point. So my x is vector of x1 until xn. My beta, I have beta 1 until beta n. My y is just one value of y. Okay, that's for multiple x case. Previously, it's just two bases. Phi equal to 1 and phi equal to x. This time we have several phi. So residual, for just one point, residual equal to y, measurement data or the true value, minus the prediction, summation of xj beta j, which is this one, xj beta j. Okay, so x is data value, right? So residual is actual minus prediction. What if we have many data points? I have x1, x2, x3 until xn. So x1 just equal to 1. x2 just 3.25 minus 3.25, 3.25 minus 3.25, and so on. xn is just minus 2.5, minus 50, minus 2.5, 0, 2.5, like a sine curve or something. And y, that's a y value. So when we have multiple variable, this time we have x several times. I mean, that is for first data point. That is second data point. And we have how many? M data point. Okay. N is the number of independent variable. Okay. For linear regression, we have just two, right? Phi 0 and phi 1. If you have phi 0, phi 1 equal to x, and you have x squared, x cubed, and so on. So this means you have many independent variables or many bases. The number of bases is n. The number of data point is m. You need more data than number of independent variables. So think about it. If you have 2 points, the best you can do is straight line. Right? If you have just 2 points, you can do just straight line. You cannot do something else. If you have 3 points, you can do straight line. You can do parabola, but you cannot do cubic equation, right? Cubic equation needs 4 points. Okay? So the number of data points has to be more than the number of unknown. That's what it is. Okay. How do we get beta value? Beta is the coefficient, right? If we know the coefficient, then we are done. So that's residual equal to this, y minus the output from the model. Then I have sum square error. Sum square error is sum of the square of the error. Is that clear? So residual is the error, right? Error is prediction minus true value. That's the error. Error square is error square, and you sum it, then you get sum square error. SSE. That's sum square error. Sum square error, if you write it down, is the summation of yi, which is true value, minus model value. Okay? You take the absolute and then you square it. And you add each of them together. How many times do we add things together? M times. Equal to the number of data points. If we have 1,000 data points, we add it 1,000 times. So we compare the model prediction minus value of 0.1. Okay, square it. Plus model prediction minus value of 0.2. Square it, add together. Plus model prediction minus 0.3 value, square, add them together. Do it 1,000 times, or m times. So S, sum square error, can be written as norm of vector y minus vector x and beta. So S, how does it look like? Is that a square matrix? Is x square? No. I have n column and m row. It's not square. Okay? It's like rectangle shape. It has to be more row than the number of column. That's for your x. More row than the number of column means you have more data point than the something that you try to fit. Okay. Why do we use sum square error? We want to find a line. Think about the linear line. Forget about other x. Okay. Forget about, let's say we have just 2x. And the first one is just 1 and the second one is just x. Forget about something else. So we try to have line equation. We said, hey, the line equation, the best fit line is a line that have minimum sum square error. Why do we have to use square? Why don't we say, hey, absolute value minimize the summation of the absolute value? Is that better? It's not better. Okay. Look at this. I have this part, this part, this part, this part, this part. Blue part. I have what? 8 of them. What line is the best fit? Between line A is that line, and line B is that line. Which one do you like, George? A or B? B is better. It's best fit. It's kind of in the middle, right? B is in the middle. So if you just add absolute value of the error together, what do you get? So for point B, absolute value is a distance, perpendicular distance, right? Perpendicular distance will be that plus that, right? Plus that, plus that, plus that, plus that, plus that, plus that. That's for B. For A, you have the same thing. Instead of, you may have 5 plus 5. In A, maybe 2 plus 8. Plus 2 plus 8. 2 plus 8 is 10, right? 5 plus 5 is 10. So sum of the absolute value maybe, let's say 10, 10, 10, 10, 40 for A, and also 40 for B. So if you just use absolute value, you cannot tell which one is better. Make sense? So if you just use absolute value, it doesn't tell you. If you use square, square is area. So for case A, you measure the distance, right? And you square it. Square it equal to area. This is distance between line A and that point. What about line A, line B, line A and that point? So you have that area, right? This line is the distance, this tan square is the area, you have that. This is area from those 2 points. What about B? B will be this line, this area plus that area. Red and green. I put them on top of each other and you can see. Small green plus big green is larger than medium square plus medium square. So if you are in the middle, sum of the square is going to be minimized. If you are off the middle, then it becomes bigger. So this time sum of the square can tell you which line is the best fit, right? So that's why we don't use just absolute value. Make sense?
What kind of software that you use to plot?
I just use. I didn't do any software thing. I just use a LibreOffice presentation, which is the same as PowerPoint.
Oh.
No special software. Just plotting by hand. All right. Let's take a look at the math part. We want to minimize some square error, which is s. S is a function of beta. What do you think? Look at s. S is y minus x beta. Y is given, right? It's a true value. Correct? X is, in this case, it's kind of given, is a data point. Or it's a basis, actually. If you do linear, you have 1 as the first basis, and you have x as the second basis. If you do quadratic, you have x squared as another basis. If you do polynomial, fourth order, you have x cubed and x to the power 4 as the next basis, right? Okay. So x is a basis based on the function that you use as a basis. But we'll talk about that later. But basically, that basis is kind of your guess. You just put it in. What you try to find is coefficient that make your model fit. So let's say your model is 1 plus x squared plus x cubed. So that's your model. The question is, what is the coefficient? It's 1 multiplied by what? It's x multiplied by what? It's x squared multiplied by what? So that coefficient is beta. How do we find beta? We find beta such that s is minimum. Minimum value means differentiated, make it equal to 0, right? So ds by partial derivative of s with respect to beta j equal to that. Math part, is that important? Yes, it is. So that when you read a more complicated model, you understand it. So we should talk about it. So this is what I copied from the previous slide, right? And I just take the derivative with respect to beta j. Okay. What is this summation? So I have I equal to 1, I equal to 2 until I equal to m. I equal to 1 is y1 minus summation of j equal to 1 to j equal to n of x1j bj plus y2 minus summation blah 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 until yn minus summation of j equal to 1 equal to j equal to n of snj beta j. I just expand this term. Okay, partial derivative has the rule that if it's not a function of beta j, it's equal to 0. You can see that y1 is that a function of beta j? No, it's not a function of beta j, right? But everything is all together inside the square. So that's why we say, hey, only for the case where j, what do you do? So from this whole thing, it collapsed to be just this, okay? So for example, we have just xij, beta j, and this is yi. Everything square. We don't have this summation anymore. Okay? Where's that? Where should it be gone? Can you help me with that? Ami,
Sorry, come again.
how do I get from this line to this line?
So basically, you so I equals to 1.
Okay. Okay. What is that 3 point?
Since
Yeah. Since d by d beta j of just that term, of just one term, okay, of just one term equal to that. Do you agree? Since, so no connection. Since d by d beta j of just one of that equal to this. How do I do that? I take 2 over here, right? So that's how I get that 2. Okay. What about d by d beta j of yi? Is that 0? Yes, it is. So this is 0. What about d by d beta j of that summation? I just leave it like that. So it's like u square. d by d beta of u square is 2 du by d beta, just that. So I leave it like this. Oh, what is r? Okay, I need pen again. d u square by dx. I will get 2 u du by dx. You agree? So what is that 2u? That is 2u. Okay? And that is du by dx. It's over there. So r, what is r? What is I? What is I?
should be the rule.
That is I. yi minus xi j beta j. So it's a base for square, right? Is this whole thing. Okay? Take the derivative with respect to beta j equal to 2. So 2r stay. So this term just get minus xij. Why is that?
Because the derivative of bj would be 1.
Only for the case where beta j that survive. If this thing doesn't match, d beta 1 by d beta 2 equal to 0. d beta 2 by d beta 2 equal to 1. d beta 3 equal to by d beta 2 equal to 0. So only for the case where beta equal to j it survive. Otherwise it's equal to 0. That's how I get just one term. Alright? So d by of just that equal to this. But I have multiple terms. Right? What do I do? So instead of no sigma, I kind of put d by d beta j inside the summation. So I take the summation out and I do that thing first. So I will have sigma m, sigma I equal to 1 to m of that minus 2j. See my point? So this summation sign, which is that, stay. Because I just showed you how do I take the derivative of just the inner part. Right? I take the derivative of inner part, that equal to minus 2ri xij. So when I have summation, just put summation back. Then I have this. So expand it a little bit. R is y minus summation of x beta. That is y. Right? So for minimum of some square error, that term go to 0. 0 means just put this whole thing go to 0. So I have 0 equal to, so minus 2, I've divided both sides by minus 2. 0 divided by minus 2 equal to 0, right? So I have just that. Okay. Now let's take a look at this term. See this? xij, yi multiplied by xij, I get xij yi, right? So this xij have to multiply by that and has to multiply by that, right? Make sense? Don't sleep yet. Okay. Xij multiplied by that and by that. So for the first term, I have this. So second term I have this multiplied by that. So this means once you put this inside, you move one of these to another side, you get this term, right? Summation of xij yi equal to double summation, which is come from this term, okay, of xij, xik, beta k. How many equations do we have? Many. Is that many? M equation. Okay. So we have many equations. M equation. So this is only for one j value. I mean, actually we just did partial derivative with respect to beta j, right? So that is to find just beta j. We need to find beta 1, beta 2, beta 3, beta 4, beta 5, beta 6. So we have to repeat this process. We will have n equation of that. That's just 1. But we have n of that because we have n coefficient. So the explanation here, I say, we actually have n of the above equation. J equal to 1 to n. Okay. X is m by n matrix. Y is n by 1 matrix. And beta is n by 1 matrix. So when we do it n times, we have this equation, but we have n times. So I can put in matrix format. Both form is vector. Okay. So instead of writing it like this, I change from summation of I equal to 1 to m of xij yi to x transpose y. Okay. So this means we have n equation of that. X transpose y is n by 1 matrix. And I will show you what it is. And I have, instead of writing it like this, which is for one beta, when I have multiple beta, I have x transpose x multiplied by beta. That's for n equation. But it's very difficult to understand what is, how do we get x transpose x equal to summation xx. Let's take a look at it. X transpose y. So that is x transpose y. Typically x is x11 and x12, right? But this time we transpose that by that become 2, 1 instead of 1, 2. So this matrix is x transpose. That is y. So when you multiply this row with that column, we get the first member. We multiply that row with that column, we get the second one. So naturally, if I multiply that by that, what do I get?
You get one number.
Which is this one? Okay. I just get one number. It's the summation of I equal to 1 to m of xi n yi, which is that multiplied by that, term by terms. Okay. Take a look at this. This thing, is that the same as that? Is it? Yes? Yeah. Look, summation I equal to 1 to m of xi n yi. Same. So for n equation, this term become that. No doubt. As proven here. Good? Josh, are we good? Okay. Now let's take a look at x transpose x. X transpose, we just have 1, 1, 2, 1. And this one will be 1, 1, 1, 2. That's the difference. It's just flip like that, right? So what do? Let's just multiply it. That's what we want to do. We multiply this row by that column. I get that index stay the same, right? For the first one. So that's why I have that. The first index at the bottom, second index stay the same. That is that. So the first term we get summation of 1 equal to I to m of xi1, xi1. That's the first term. Second term will be first row multiplied by second column. So I have xi1, xi2. And I keep multiplying every component. I get that. You can do it like that too. It's just long. But how do I understand it completely? Just do it. Right? Like Nike, okay? Just do it. You get that. So you multiply this with that, then you get that term, right? Correct? I just shorten it by use a summation notation. Good? So let's take a look at that term. Where do I get that from? Row n, column 2. So row n, column 2. What I want to take a look at is like, what is the size of matrix X? Size of matrix X, how many columns do we have? Naturally, how many columns do we have for X? How many rows? M. So it's not square. But after the multiplication, is that square? At the end I have n, right? Initially it's not square, it have n column and m row. After the multiplication, it's square. Good? So that is x transpose x. But that's not our final goal. We want x transpose x multiplied by beta. How's the beta? Beta is column vector. You just multiply it. Nothing special. You just have to write a lot in order to follow it. But I put it on computer, maybe just copy and paste and change it several components. So you have that multiplied by that. Equal to first term, right? Have that multiplied by that. You get second term. Have that multiplied by that. You get the last term. So that is your x transpose x multiplied by beta. And if you check, you have summation of k equal to 1 to n, I equal to 1 to m of xin, xik, beta k. Are they the same? I equal to 1 to m, and then here I have I equal to 1 to m, k equal to 1 to n, k equal to 1 to n, right? xij, xik, I have xi, oh where's my xij? Not the same, xij, xik, beta k. I have xin, xik, beta k. So it doesn't, there should be k equal 1. Oh, that's a little bit different, I think, because of the typo. So, I think I know why it doesn't match. Because this is for row n. Previously is for row J. Right? This is for row J. If this is at row J, what are you doing? It's not time yet. Don't pack your bag. Stay with me. So this is at row N. That's why you have N. If it's at row J, this will be J. So XTX beta is the same. I mean, it's not the same, but if you have this equation N times, then in the matrix form, you get X transpose X multiplied by beta. Got it? So the closed form means, if you want to find every unknown, you have to solve one equation. Left hand side is X transpose X multiplied by beta. Right hand side is X transpose Y. We get this, right? X transpose Y. And we get this XTX beta. But we have just one, because that is just one beta. If you have multiple beta, you have this. This is the same as system of linear equation AX equal to B. A is n by n. Beta is unknown, which is x, right? B is column vector. X transpose Y is a column vector. N row, one column. Can you solve it? Daniel, can you solve it? How can you solve it? Which method are you going to use? Come on. You said you can. Keep your promise, please. George?
AX equals to B, right?
You can multiply both sides by A transpose, or not A transpose, A inverse, or you can use Newton-Jacobian. Did you study that? Did they teach that? Newton-Jacobian? Oh, no, not Newton-Jacobian. Gaussian elimination, I'm sorry. Use Gaussian elimination. LU decomposition. Can you use Cholesky decomposition? No, you should not. It may not be symmetric. And you should do partial pivoting. So X transpose X is dependent on how many number of data points you have, right? You always have n column, but as many row as number of data points you have. So that's when you have that. That's how you calculate J. So in this case, X is ATA, B is XTY, X transpose Y. All right. So after setting X from degree 0 to degree n, so now we define our basis. We say, hey, X is X to the power of 0. And this X1 is X to the power 1, X to the power 2, to X to the power n. We need that. We need that. 1, 1, 1, 1, 1, 1. We need that. Do you need it? Yes, you do need it. Otherwise, your matrix won't be, you don't have like intercept, right? So you always need that. Column of just 1, 1, 1, 1, 1, 1. So this is your basis. And you have Y value, so you do polynomial regression. Do you need to do polynomial regression? No, you don't need to. It can be linear combination of constant beta 0 plus constant beta 1 multiplied by sine x plus constant multiplied by sine square x plus constant multiplied by sine multiplied by x cubed or something. So basis doesn't need to be polynomial. One special case is polynomial. And we solve it. Then we do linear regression. If you want to use polynomial feature, I mean the sklearn, polynomial feature make this matrix for you. Okay. Polynomial feature means you come with just one x, it makes several x for you. That's polynomial feature. Make just one input to be like order n. Okay. So polynomial feature is pre-processing process. So you import polynomial feature. Okay. Second, you create a variable to be that class. So you say, hey, poly is polynomial feature degree equal to 3. So this poly is an object. Okay. Then I use class method to create polynomial matrix. I say, hey, x underscore poly equal to poly dot fit transform s dot reshape minus 1 1. Reshape minus 1 is 1. Minus 1 is automatic. So reshape, the first member is number of row. So minus 1 1 means automatic number of row, but just one column, right? So whatever I get, I don't care. Reshape it to make it column vector. So poly is the object, right? Object of polynomial third degree. The fit transform is kind of fit with the data and it transforms. So basically, it creates this x poly to be these 3 column, okay, or 4 column. So that's how I get that x. And I have, okay, x dot reshape is to make a column vector. X equal to x1, x2, x3, x4. X dot reshape equal to bracket of that minus 1. So we will see more in the code part. Okay, and at the end, we do this fit. Just that. If you want linear, you just green line is your linear. If you want 8 order, you can use degree 8. Okay, we'll go that.
So it's just fitting one point at a time, like on every point, right?
It fit every point one time. Use that close form, right? I think it's a little bit over time. Oh, it's 12:20. We are on time. Okay, goodbye. See you next time.